Hi everyone, I'm Chris and welcome back to this machine learning course. This section is about batch normalization. The idea behind batch normalization is similar to the normalization of the variables in preprocessing the data. Normalization scaled the variables to a comparable value range. As sketched on the left side, this leads usually to a smoother gradient-based minimization. Now, this idea is transferred to deep neural networks. The idea is to consider each layer of neurons as a model with individual normalizations. So each layer takes input values which are output values of a previous layer. A normalization of all output values of a layer would normalize the input into the next neuron layer. Note that the input variables x should be normalized anyway. This batch normalization approach can lead to a smoother and faster training of the neural network. This is because the layers are more decoupled and behave more like individual, more shallow networks. Instead of normalizing the output values, the normalization can be applied one calculation step earlier. The normalization can be executed before the activation function is applied. This option is considered in this section. So the normalization is applied for the summation variables. The summation variable for this neuron on the right side is Zm superscript 3, and it's a linear combination of the outputs of the preceding neuron layer with the corresponding weights. Further, a bias term is added. Then the normalization is applied. And after that, the result is put into the activation function, which gives the neuron's output. Typically, for normalizing the layers, standardization is used. This means the values of a neuron summation are scaled that they are distributed according to a standard normal distribution. Let's consider a hidden layer number capital T with capital M neurons. This layer has capital M summation results from linear combinations of the outputs of a previous layer with weight parameters. So each of the layer's neurons performs a summation denoted by Z1 up to Z capital M. These summation functions are normalized individually. The mean and variance for one of the neurons M is calculated for a mini batch of capital N data points. So for capital N data points, the summations in the neural network are calculated across all layers. Then, the mean and the variance for each summation variable Z is calculated for the capital N values at this point. The mean for the mth neuron, μm, superscribed by the layer number capital T, is equal to 1 over capital N, the number of data points in the mini-batch, times the sum over all of these data points of the summation value for the nth data point at the mth neuron, Zmn. The variance at the mth neuron is sigma m superscript capital T squared, and this is equal to 1 over capital N times the sum over all data points of the mini-batch of the square difference of the summation value for data point and the mean. So using mean and variance at a neuron, standardization of the corresponding summation for the nth data point is the summation of this data point Zmn minus the mean μm over the square root of the variance plus small epsilon. Note that this small constant epsilon in the denominator is added for numerical stability. Standardization shifts the values by the mean and scales them by the standard deviation. Then, the values are distributed according to a standard normal distribution. We can apply this standardization technique for each neuron, layer by layer. But the input into the activation functions, so the standardized summations, should not be limited to mean 0 and variance 1. If necessary to fit the training data, a different mean or variance should be learnable for the neurons. Therefore, to restore the representation power of the network, parameters gamma m and beta m are introduced for each neuron in every layer. The gamma parameter can rescale the variance, and the beta parameter can reshift the mean. These new parameters are trainable like the weights of the neural network and allow to take different means and variances into account. Note that the backpropagation algorithm needs to be modified to optimize these parameters gamma and beta in addition to the weights. You might wonder why to apply a normalization when there are parameters which can compensate this. We will not go into the various details to answer this question, which is still under debate. Here we will just make a loosely argumentation. So neuron layers are strongly coupled. The output of one neuron is the input for another neuron in the next layer. This input is scaled by a weight, and after passing the activation function, it is multiplied by another weight of the next neuron. Therefore, a weight update of a parameter can affect other parameters and their updates in subsequent training iterations. This is like a distortion propagating through the network. These distortions can be amplified across the network, similar to the increasing variance we have seen in the previous section. Now, batch normalization can decouple the weights a bit by controlling the distribution properties mean and variance of a neuron's summation directly. This, loosely speaking, damps the propagating distortions. However, if necessary, in subsequent iterations, the distribution properties can be readjusted. Thus, the training process is more stable. So the training with batch normalization adjusts the weight parameters and additionally controls directly the distribution properties. Section finished. Thank you very much for listening. If you like this video, please click the like button and consider to subscribe this channel. If you have any questions or comments, please leave a comment down below. So thanks again and see you in the next section.